So thank you all for joining. This is our second webinar in the Pipeline Week, and we have Bill Reed, who is the Associate Director for Science Operations here at the Sophia Science Center, talking about the FORCAST Grism pipeline. So thanks, Bill, for joining. Tomorrow we have a similar webinar, 9 a.m. on Hawk Plus processing, and on Friday it's going to be on FIFI-LS. But a few things, the meeting is being recorded, so it's going to be posted online in a couple of days. And if you have questions, please put them in the chat, and ask them to Bill and other Sophia staff when relevant. Bill, you can start whenever you're ready.
Okay, yep, and just to be clear, the questions are going to be monitored and read by you.
That's right, if that's okay.
Thank you. All right, well, this will be short, and the intent is to give a demonstration of running the Sophia pipeline, which is released publicly as open source code on a particular example of FORCAST Grism spectroscopy. So if you were in part 1, and if you are at all interested in reducing Sophia data, you know how to get it out of the archive from URSA, which is a very straightforward interface. If you were to type in the source alpha her and instrument forecast and spectroscopic mode, you'll easily find these data. Download them to your computer. And if you were to, now when you want to reduce data, you need to get together or identify the files that have the same mode, the same observing mode. So in this case, we're going to be reducing Grism spectroscopy data, and we need the FORCAST Grisms. There's a set of them, different instrument configurations and calibrations for each one. So you want to find the ones that are the same. One way to do that is you just need the raw data. One way to do that is I just use this thing called GetHead, which is from the same team at CFA that made DS9 and SAO image. But you just need to look through the header keywords. There's a huge number of them. I find these ones that we made up on Sophia called SpecTel1 and SpecTel2 are super useful. So if you just look for all of the files in that directory that you get at the SpecTel1 and SpecTel2, you can see that there's a set of them that have, it's called 4_F112, that's filter imaging, and the 11.2 micron filter, and 4_G227, that's Grism spectroscopy nominally, in the other filter wheel. So if you go down, today I'm going to demo looking at the 6.3 micron region Grism. So here are the ones where SpecTel1 was equal to G063, the 6.3 micron Grism. All right. So then, let's see. So I wanted to do a combination of a live demo and also, and also just showing you some static results. So that one I wasn't going to show you me doing LS on the screen. Now I'm going to go ahead and boldly switch over to a live demo. Let's see. So I'm just going to share the screen. All right, so now you're going to see a huge amount of stuff on my screen. And this here, where I'm circling, so this is Redux. This is the pipeline as developed and as you can run in a convenient graphical user interface form, which has its own complete and very clear set of installation instructions. And the lecture yesterday was about that. So if you've got to this one by mistake, you can go back and watch the previous one. And if you need help with installing it. So to run this, you just say open new reduction, and then you need to find the files that you wanted to reduce together. And that was why I showed that thing before where you're deciding which ones. And what it said, the thing that I had circled in the blue, in the cyan circle before was, I think it was 61 through 66, were the ones that had the G063 Grism. So you just open those. There you go. There's this display that you can get here. I find you get it by turning off update displays, which shows for those 6 files, it shows some of the most handy header keywords. You can see that it's Grism spectroscopy in the short wavelengths channel, scooting way over to the right. Here are those 2 keywords that I was using to identify the mode being used for each file. The altitude, so this was actually quite low, 36,000 feet. And zenith angle, exposure time. All right, and then these keywords here at the end are put here because they're critical for the operation of the pipeline. You can see that there's this thing, Dither Index. It says 1, 1, 2, 2, 3, 3. So there were 2 dithers done. And then nod beam goes AB, AB, AB. So, and 2 nod positions. All right, so what we should see is the source moving between dithers and, well, between dither 1, dither, and between the nod beams. All right, let me put that back to update displays. And the general, I mean, you can just press the reduce button and it'll go all the way through, and you should get something similar to what came out of the pipeline, assuming that, and you can read release notes, the QA notes, to determine if this was true, assuming that all the files were good and were included in the actual pipeline run. But if you're just going to look at things at a one-by-one basis, you can step through using the graphical user interface, the various steps, and there is a way to get an XPA interface working to display the images from each step in real time. And that does work, but it's a little complicated. Well, just on the software side, it's complicated. It's really easy to operate when it works. But what I find is just as easy or easier is to just make them anew, and let's see, edit, save output, yes, this step, and then just look in your output directory, and then I don't know if you can see those appeared in, just now. Select them. I already had a DS9 open. Let me close that and reopen. Okay, and there we go. So you just select the 6, and this is how I do it. And so now we see here's the 6 images. They look a lot better than before already. As you saw in the PowerPoint, there were, oh yeah, so let me go back and re-emphasize that, which unfortunately, I'm gonna stop sharing, restart sharing. Okay, where did it go, PowerPoint? Alrighty, let me go back to the static for a minute. So the raw images look pretty much like this. And there's all kinds of weird artifacts in there. You can see the source here. So the wavelengths go in the horizontal direction, and position along the slit goes in the vertical direction. So something that's at the same position on the slit but at a lot of wavelengths, that's a star. And something that's every position on the slit, and that's at some wavelengths and not others, that's the atmosphere. So these are atmosphere lines. These white vertical things are atmospheric features. And the horizontal thing here, that's the star. And you can sort of see it in all of them, but more or less depending on all these hideous artifacts. But as you saw, so this I already showed you with the live demo, and then I showed you popping this up. Just the first steps of the pipeline, those things subtract out very well when you subtract the nods. All right, so here you are, the bad pixels are masked, and a lot of the gel barring and other instrumental artifacts, you can consider them essentially as dark or instrumental artifacts, or electronic artifacts, are readily removed. Okay, so there you go. And in fact, you can see the source did not move much between these two and these two and these two. So there's really just three observations with essentially 2 repeats. Okay, so now I wanted to show you, so what can you do besides having the fun of pressing the run button successively to see the steps? And you do have the advantage of seeing the new intermediate files come out as long as you have the, well, just a second. You can see the intermediate steps. So if you go to a step, you're just about to run a step. So here we're just about to run the make profile step, which is actually where I paused the live demo. And you press edit, then you can see the parameters. So these are the control parameters. If you were running in the command line mode, then these are the things that you would be entering. But with the graphical user interface, it's just very straightforward to do. So there is a calibration file. There's a slit correction file. This is not calibrated yet for FORCAST. There's a polynomial order that one can control. This step is making the spatial profile of the source, basically to locate it on the slit. Whether one subtracts a background, whether to ignore places where the atmospheric transmission is bad. So you can control those things. And then this top one, which is really the reason I wanted to show you this. Sometimes that's checked and sometimes that's not. Not every intermediate file of every step is saved by default, but there's no reason you can't. You just have to do the edit and then check this. If you do that, then they're going to appear in your directory, in your output directory, and you can view them in DS9. All right. If you proceed to the next step, well, actually, then go back to live. All right. Stop sharing. All right. Where's Redux? All right. So we'll go to the stack step, which we'd already done. So we have that. Make profiles. So that's where the PowerPoint was. Just takes a second. So in this case, we have an output window that appears, and for each of these 6 input images is giving us a profile. This is actually fitted from the data. It's just very bright. The sort of alpha her is just a very bright source. You can see the location of the source. So it's at position about 123 or something along the slit. And there it was well located for all of them. You can see that there were the 2 pairs at the same location. Then this one was slightly offset, and then this one was offset. So there they are. And now what we're going to do, because we're doing spectroscopy, is we're going to locate the source. So this was a crude version using the average profile. Now we're going to locate it and trim so that we can correct for the location of the source not being straight, so the spatial calibration not being perfectly straight across. And then we're going to set where to integrate when we do an extraction of the source. You can actually just already, if you want to just see the spectrum of your source quickly, you can just bring up any one of these reasonably early intermediate steps. Let's just say frame single, zoom fit. And so you can already see there, here's the source. You can see a lot of little black and white regions. There's obviously a lot of spectral structure. It's not perfectly straight, but just to do a quick thing, you can region shape projection and turn on regions. You can actually just use DS9 and make a quick spectrum from that, just to see what's going on. So when you can do this, you can't do it very well from the raw data because of the electronic artifacts, but with any of the intermediate files, it's pretty straightforward. There, we can do like a super crude non-background subtracted source extraction right there. So that's what the answer is probably going to look like, but we're going to do much better. We're going to take into account the curvature of the source, and we're going to subtract the background using just above and just below. So that's what we're going to do with the pipeline. So let's get back to actually running the pipeline here. So locate apertures. So now it has definitely found where the source is. And trace continuum is going to find where it is for each spatial position along the slit. This one takes a little while. Oh, okay, I see a bunch of TRC files are there. Okay, so that's actually done. It didn't take very long at all. All right, set apertures. So now we have all the little dotty lines here, and they're indicating here's the source peak, and then the small dot lines are showing where we're going to average between the small dotty lines to call that the on of the source, and then for the off, we're going to average between the dotty line and the dash dot. Okay, so those are going to be our reference region. So the background will be estimated from that, and the on will be estimated from that. These are controllable. Let's just mess with them now. So we can undo that, edit this, and let's save the output. We're not going to extract full slit. And let's say that we're going to make an aperture radius. It's going to be in this same unit. So let's make it 10, just to make it big. And background regions, you can actually control where they are. I'm not doing a recommended reduction here. I'm just demonstrating control over the software.
Bill, can I ask you, when you're changing the aperture parameters and you run, does the pipeline create new files in addition to the ones that were created by the previous run, or it overrides them?
It's going to make new ones with the same name. So yes, overwrite.
Okay,
So yeah, so well, I just have it here. I just have my output directory open with sort by date, and then this step, set apertures. I I turned on the output saving for this one. So that's, I guess those are called APS. I've never actually looked at those before. But there's those, and now we can see that there's a red line here. So now we can see the background regions are actually done. They're not automatic. And I made the on much fatter. All right, so I don't know if I explained all the symbols correctly, but now it's pretty clear because we controlled it by hand. Between 75 and 100 and 150 and 175 is what I said is the background region, and it's actually this. It looks like this is the on region here. Is between these symbols.
Bill, right. Is the curvature of the spectrum automatically taken into account?
By this stage, yes. Well, we haven't done it yet, but it will be during the extraction.
Okay.
So now I can run this subtract background step, and let me see in the output. Look at the output directory. All right, nothing new came out. So let's go back and check the parameters for that. Yeah, it didn't have save output set. Let's run that again. So now we have BGS files, which I've never looked at, but let's just take a look and see what they are. Close my old DS9, a new one. So they're probably the same, except it's probably near 0 in the background region, which it is. It's about 0 there, and on the source, it's 1 or something. So you can clearly see it did something. It did the background subtraction. So now we're going to get out of image land, and we're going to move into where we wanted to be, which is in spectrum land. So we run extract spectrum. It's going to use our background region and our on source region, and now we're in this window, which popped up as a default within Redux, and you can see a spectrum. Okay, and one thing I'll say is when you're doing spectroscopic reduction inside of the atmosphere, so not from a space telescope, hold your breath when you make the first reduction, because those features are mostly probably not real, and true to that, none of these are real. But they're real in the sense of they're real data, but they're mostly caused by the atmosphere. All right, merge apertures is in the case where some of the orders overlap on the slit, which doesn't happen here. So this is one of the main steps. It's called just one thing, Calibrate Flux, but that can lull you into a sense that it's not doing much except multiplying by a constant. It's actually doing quite a lot. It's doing both application of the spectral response, the calibration of which I can explain if requested, as well as the atmospheric response, the atmospheric transmission correction. So you can actually see which response file is being used. You can change it if you have another. For example, if the instrument scientist says, "Why don't you try using this attached file?" then you can use that. And then the HRAN directory. So that's here. There's a default one here, and on the documentation for Redux. Go back over here to GitHub. Oh yeah. So on the documentation page, there is, let's see, HRAN. Yeah, there's an explanation of how you can actually get the better atmospheric models. So probably recommend that if you're trying to do a really good job. Okay, and there are various other parameters. Not going to go into that. That's all. All of these are documented in the FORCAST pipeline user handbook. So for now, we have the save here. Let's go ahead and click this, save the spectrum as well, and run. And now let's go to our output directory and see what we got. So what we got out of this step was the CRM files and CAL files. So the CRMs, let's open those. I'll close my old DS9. Let's open the CRM files, 2, 4, 5, 6. Okay, so these, as you can see, are beautifully cleaned, background subtracted. Actually, are they background subtracted? Oh yeah, now they're in physical units. So those numbers are near 0, the ones that are around 0 or 1. But now the source in these same units is hundreds. Okay, so there's the CRM images. These can be used for custom extractions. I actually recommend if you're doing a custom extraction, you might want to use those. So, but if you're using the pipeline extraction method, that would be for extended sources. But for point sources, the pipeline does the extraction, and then you have this file called _cal. Obviously, we're not going to open those in DS9 because they're spectra, they're 1D files, but you can open them. Open them in DS9. Let me see, what directory am I in here? Right. Expand this. So now in the window down here at the bottom where the mouse is moving around. So let's just try reading in one of those. And just, you want to plot them. Obviously, we already have, the GUI has already made a plot. I want you to have the power to do what you want in Python too. So you can read in the normal commands that one does to read in a file into Python. I'll do it in Python. Okay, so the first and second columns are wavelength, and flux, which you can learn from the user's manual. Yeah, okay. Let me just make sure that we're, stop that again. Okay, yeah. So there it is. So looks about the same. So this was one spectrum. I opened one cal file, one file that was with the _cal in it, and this would be one of the things that's being shown here in the Redux GUI. The Redux GUI went ahead and overplotted all of them. Okay, so we're down this combined spectra. So that combined them in the 6 into 1. And this last step, it says run make spectral map. It actually isn't a spectral map. So you'd think, oh, it doesn't do anything, but it does one thing, which it does make the preview image, which is nice, which looks like this. So this is the final result of the pipeline, not the FITS version, but the summary version that's used as a preview image. And we're populating the archive with these so that observers can get this. And there's a huge amount of information here. One, you can see your spectral image. So here again, wavelength and spatial position. And then here's the final extracted combined co-added spectrum in the histogram style plot here. And then overplotted on that is the atmospheric transmission. Oh yeah, there's a nice right-hand axis scale. So looking at this now, trying to interpret this, you'd look at it and say, okay, well, looks like there's a positive looking hump here, and there's a nice narrow dip here. But as I was saying, as we were going through this, definitely hold your breath when doing spectroscopy, and you need to pay attention, especially to this step right here, which is comparison of your spectrum to the atmospheric transmission, because the first order version might not be right. And there are some features that we cannot subtract. In this wavelength band, we can actually do quite a good job. In the next one over that includes the 9.6 micron ozone feature, you can almost never calibrate that out. It's just, it's almost completely opaque. Technically, this band, which is a band of methane, technically it had 60% transmission if our calibration was right. But we did suspect that there might be something wrong, and that's why I use this as an example, because I just remembered working on it. I'm going to switch back to PowerPoint here. I guess I could have just maximized PowerPoint.
Bill, quick question. That's usually the nasty one. Do you have uncertainties at this stage already?
Oh, yeah. So not plotted here. So this was to overlay the 6 to get redundancy. Then in that step after co-adding, yeah, like in this one, I guess we could have plotted it here, but when plotting it yourself from the combined co-added spectrum, it's a number of wavelengths by, I think it's 5 file. In the first one of those 5 is the wavelength axis. The second one is the flux. Third one is the uncertainty. Okay, and I forgot the order of the 4th and 5th, but the 4th and 5th are the atmospheric transmission, which is plotted here, and also the spectral response that was used is one of the axes. So the idea and the principle that we had in developing the pipeline and its output products is to be as self-contained as possible. So really, you could have just taken your product right out of the archive, and you could see all those things. But yes, that's right, Bernhard. There is an uncertainty array that's made with this.
And
yeah,
go ahead, Bernhard.
Sorry, yeah, the follow-on question there about the uncertainty. I mean, I don't want to drill too deep here, but that's of course always the important bit, really, when you want to do science. So I mean, there's a statistical uncertainty, of course, but then there is also an systematic uncertainty coming from, for instance, these things like atmospheric transmission. And so do you treat them separately? Do you treat the systematic at all? How do you go about it?
Yeah, unfortunately that's going to be beyond me. I know that there is an attempt, but I would have to read it very carefully to find out how much I would take it.
Got it. Okay,
yeah.
Thanks. Yeah, no, but these are of course the things that you need to get your wrap your head around.
I can address that if you like.
Oh yes, please.
So the error plane that is tracked with the spectrum is the statistical uncertainty that's propagated throughout the pipeline alongside the flux. There is also a systematic uncertainty. We don't include that in the error plane, but we do track it separately as a header keyword, as an overall percentage of error on top of the errors, the statistical errors. So that's detailed in the user manual for the pipeline. So you can look for that, but the keyword for the header is cal_err.
Thank you, Melanie.
Cool, thanks.
Right. So, all right. So, as a spectroscopist, which you are, if you're interested in looking at this, then you're wondering. Look at this. I'm saying that my star happen. If I believe this as a real feature, I'm saying that my star has a feature at the exact same place as the atmosphere. Yikes! You got to be really careful with that. Right, yes, it's showing that that is the telluric absorption plot, and look out. So if you want to check all of your parameters, there is just, you can save your configuration parameters into, and it's just in a text file, very easy to understand. You can see what are the things that you can control. You can find out what are all of the input calibration files that were used. So this is super useful, especially if you make a bunch of custom edits. Like I made a weird edit to our apertures, for example. You can, and if you want to use that for a bunch of sources later, you save it as a configuration file. Then you have it, and you can read it back in. So if you're curious about what that feature might be, well, you have to do some hunting, because already this has gone through one set of expert eyes, which is the instrument scientists doing the reductions right after the flight series. And they have a couple weeks to reduce everybody's data from the series. So they do spend, they are experts in running this, but they do have to do all the calibrations and then the application to everybody's individual observations, of which there can be quite a few during a series. So they're not able to put a huge amount of time into each observation, but it's already gone through one set of expert eyes. So don't expect it to be something super easy. So that feature, we to be skeptical, one has to be skeptical as a scientist. We consider it to be spurious, and then go back and prove that it isn't before we publish it. You can look, so you look at each one, you can see it's in every single spectrum. It's not introduced by just one, and that you can do by looking at the 2D images or at those 1D spectra one by one, or just in the overplot that Redux GUI already showed you. You can look and see whether it's in the instrumental response. You already know what's in the atmospheric transmission. If you look at the step 14 input parameters, it says rest file equals. So just right before coming onto this, I just opened that exact file and plotted it here. And yeah, there's definitely some weirdness in there. It's probably not a piece of methane in the window. Could be. We don't know. Well, we do know it's not, but in principle it could be if you don't know what the instrument's made of. You can go back and inspect the calibration data. So this is something I highly recommend. You can get, if you're really curious about something, you can go back and look at the stars themselves and reduce them the same way. And you can also just divide your source by the star directly, like is done in a lot of ground-based astronomy. You can verify the wavelength calibration. You can do that by looking at the two-dimensional images that show atmospheric features, especially in the CRM that's already been wavelength calibrated. And then you can see, do they match the place where ATRAN, the atmospheric model, tells you there is an atmospheric feature. And if they're not, then you're going to have to shift your data to match it. You're going to have to update the wavelength calibration. And then really, the instrument scientists are here to help you, so you can ask them. And I certainly highly recommend doing that, especially when you've already done the obvious, and now you're thinking, it looks like the atmospheric features aren't at the right place. Why could that be? And I'm sure they'll be able to help you out. Oh yeah. Okay, so we did all of the above for that project when we were helping out a guest observer, and found that if we did it with a new wavelength calibration file, actually that methane feature can be made to it just goes away. So that was nice. This one I'm still suspicious of. I bet that's nothing. And as you saw, there was also, let me go back. There's also a pretty big atmospheric thing here, which is actually incredibly annoying because there's also interesting astronomical features there. So that one I would say is still a question mark, but I certainly am not going to recommend the guest observer publish that. Okay, so this was a quick run through and partial demo of the pipeline and how to do some simple offline steps like using DS9 to inspect the beginning, middle, and end files, including both 2- and 1-dimensional products. The pipeline is very straightforward to run. You only need to download the raw data from the archive because the calibration files themselves are included in the software release. Inspecting the intermediate files is straightforward. If you watch them as they come out one after the other, you can just see what are the files that the pipeline just made and open them. And if they're a 2-dimensional image, you pop it into DS9. If it's a 1-dimensional product, like for spectroscopy after the extraction stage, you can just bring it into Python or IDL, whatever. An obvious lesson for any spectroscopy is to pay incredibly close attention to atmospheric transmission. You can inspect the actual calibration files themselves. Do not be scared of them. They're generally in a very straightforward, they're very straightforward products. If you can open any FITS file, you should be able to open the SOFIA calibration files and plot them within a minute. And please remember that the SOFIA scientists here remain ready to help. The instrument scientists are available, and they'll get to all of the requests in between their flight series. And thus concludes my demo.
Thanks, Bill. That was really helpful. I do have a question. If one wants to play with atmospheric transmission correction and use different ATRN files, do you have any tip on what range or water vapor one should use? I mean, the altitude, you showed it at the beginning, it shows up in the very first step. So that one is, I mean, you just take the altitude that is listed there. But what about water vapor? Do you use a range? Do you have any indications from the observations?
So in that flux calibration step, an attempt is already made using the line of sight, so using the zenith angle and the altitude of the plane. So that's already done, but of course there's day-to-day weather variations, or else life wouldn't be so interesting when you look up at the daytime sky. So to take that into account, yes, there's a range of precipitable water vapor values that are stepped through. And as for which one to use, no, I don't, except that you can see the range that are available in the pipeline products. No, I'm not going to bring up anything like for that. You can see the range that are available in the calibration products, and just overplot them all, right? And if you want an intermediate value, interpolate. And what something else that I've tried is just you can get your own file out of ATRN with whatever gridding and rebinning. You'll have to do that part. You'll have to do that part yourself if you don't use the files that are included with the calibrations of the FORCAST data. And you can raise that to a power law, which is the same as changing the optical depth, because the transmission is either minus tau. So if you raise the transmission to a power law, that gives you that's effectively like a range of water vapor values, but that's a cheap method. The better method is to use ATRN itself to generate different ones and interpolate between them, and that's what's done in the pipeline. But no, I think experimentation is the name of the game. That's how we do it in ground-based spectroscopy as well. the a priori methods only work to a very limited extent, and then you have to tune it for the day-to-day and hour-to-hour weather.
Okay, thanks. If there are more questions, people can unmute. Wait a few minutes to see more questions comes up.
Shouldn't be always me. Okay. A question about the calibrators that you're using in this wavelength range. Is it all stars? Are you using Rouge models or extrapolations of some sort, or some newer models? What you're doing there? And is it important at all? Because of, I mean, I can imagine that the atmospheric uncertainties may be higher anyway.
It's important for the overall spectral shape. Hey Sachin, you're on camera. Let me share screen again, or just share. Where's back to PowerPoint, didn't I? No. So here on the documentation page for Redux, there is, you were just asking about the calibration sources.
Yeah.
Yeah, here. So I just wanted to show that those are, make that bigger. Okay, the library is available, and so you can get them and inspect, overplot, determine their provenance. Let's click this. Actually, I haven't been here. No. All right, I didn't want to go there. But that's what I would recommend doing. They're large at the short wavelengths of FORCAST Grisms. That yes, they are all stars. At the long wavelengths, they're asteroids, just because asteroids have hugely have much higher flux. But yeah, the actual model themselves are provided.
Cool. Okay.
More questions? Well, if not, I thank you, Bill Rich, again. Thanks. That really helped, and I'm glad we have it in the box.